All right, today we are diving deep into the absolute core of modern AI. We're going to pull apart the engine that powers pretty much everything you see, from ChatGPT to, well, you name it. And by the end of this, you'll get exactly how this one critical piece works.
So we all hear about these incredible AIs, right? We use them, we see the amazing things they can do. But have you ever stopped and wondered, what are they actually made of? What's going on under the hood that lets them write poetry or code an app?
Well, it turns out these massive, seemingly complex models are really just built by stacking one single powerful component over and over and over again. You can think of it as the ultimate Lego brick for building AI. And if you understand this one block, you're most of the way to understanding all of modern AI.
Okay, so let's get right to the heart of it. We're going to define what this thing is and really nail down why this one component kicked off the entire AI revolution we're living in right now.
So what does a transformer encoder block actually do? At its core, it's all about understanding context. If you give it a sentence, it doesn't just see a string of words. It sees how every single word relates to every other word in that sentence. And that ability, that power to see relationships, is its superpower. To really get how it works, though, we can't just talk about it. We've got to look at the blueprint, the actual code that creates it. We're going to pop the hood and break it down, piece by piece, so you can see exactly what's going on. And here it is. This is the whole thing, written in Python. Now, I know, it might look a little intimidating at first glance, but I promise you it's actually made of just a couple of key parts. We're going to walk through this together. Before we get into the guts of it, let's look at the three main settings we can tweak. We've got input dim, which is basically the size of our data. Then numhead, that's how many attention experts we want to use, and here we're using 8. And finally, ffdim, which sets the size of an internal layer. Think of these as the main dials we can turn to tune our block. All right, now for the first major component inside our block. This is where the magic really happens. It's called the attention engine, and its whole job is to look at all the data at once and figure out what's actually important. If we look back at our code, this whole first section is handled by these 3 lines. We've got a multi-head attention layer, then an add layer, and we finish it off with layer normalization. So what is this little trio actually doing? It's really just a simple 3-step dance. First, the attention part figures out all the relationships in the data. Second, that add step, it adds the original input right back into the mix. This is super important for memory. And finally, the normalization step just cleans things up and stabilizes the result, getting it ready for the next stage. So what on earth is multi-head attention? Well, remember how our num head was set to 8? You can literally think of this as a committee of 8 different experts. Each head, is looking at the same sentence, but focusing on something different. Maybe one is looking at grammar, another is looking at the subject, a third is looking at the tone. Together, they build this incredibly rich, layered understanding of the context that one expert alone could never achieve. Now, that simple add layer we mentioned, it's an absolute game changer. It's called a residual connection. See, without it, as the network does all this complex processing, it can actually start to forget what the original input was. But this add step acts like a memory lane, making sure the original information is always carried forward. It lets the network learn new things without losing the original context. It's brilliant. Okay, so our block has used its attention engine to see and understand all the context. What's next? Well, now it has to think about that context. And that's the job of the second major component, the processing core.
Back to our blueprint. Here's the second chunk of operations. We've got 2 dense layers. That's just a standard, simple neural network. And hey, look what comes after. The same exact pattern we saw before. An add layer and a layer normalization layer. This whole section is called a feed-forward network. Its job is pretty straightforward. It takes that context-rich information from the attention step, and it just thinks about it. It performs some calculations, transforms the information, and gets it ready for whatever's next, either another encoder block or the final output.
The process here is actually pretty clever. It's this elegant expand and contract move. The first layer blows the data up into a much bigger space. In our case, from a size of 64 up to 128. This gives the network more room to find and work with complex patterns. Then, the second layer immediately shrinks it right back down. And just like before, it wraps up with that crucial add and norm step. The add to remember and the norm to stabilize everything and keep it all learning efficiently. All right. We've seen the two big pieces, the attention engine and the processing core. Now let's click them together and see the final, fully assembled block. When you boil it all down, the whole operation has this simple, beautiful rhythm. First, it uses multi-head attention to understand the context. Then, it uses a feed-forward network to process or think about that context. Pay attention, then think. That's it. That's the whole process, repeated over and over. And here's what that data flow looks like from start to finish. Data comes in at the top. It goes straight into the multi-head attention layer, gets its first add-in norm. Then, that context-rich output gets fed into the feed-forward network, gets its second add-in norm, and finally, a fully context-aware output comes out the other end ready for the next block. So what are the big takeaways here? Well, every transformer encoder block has two main parts, an attention layer to find context and a feed-forward layer to process it. And those little add and norm steps are absolutely critical for making sure the whole thing works. It's this simple two-part structure that's the key.
It's kind of wild, right? When you look at the incredible complexity of modern AI, just remember that at its very foundation, it all boils down to the clever repetition of just two core ideas: attention and processing.
We've spent this whole time deconstructing just one of these Lego bricks. But the models that are changing our world don't use just one. They stack dozens, sometimes hundreds of these blocks on top of each other. And that leaves us with a really fascinating question. What kind of incredible new abilities just emerge when you repeat this simple process 100 times over?